So let's start out this lesson by talking about what it means to be thermodynamically favored. So a thermodynamically favored process is one that proceeds without any assistance from the outside system. So it's a reaction that occurs by itself. You don't need to put any energy into it in order to cause it to occur. So some examples: water evaporating at 25 degrees Celsius. This happens naturally. Iron, if you take a piece of metal and you put it out in water in the presence of oxygen, it's going to rust. Sodium chloride dissolves in water. Another way we can kind of picture this then is to look at the opposite end of the spectrum. So our second example up there, the iron rusting. So iron rusting is really iron plus oxygen, and in the presence of water is forming iron oxide. So this reaction happens naturally. If you put a piece of iron outside with some water in it, it's going to rust. However, if you take some rust and you put it in water, it is not going to turn into iron and oxygen, because this reaction is thermodynamically favored. This is the reaction that nature tends to prefer. It's not going to go backwards, because that would not be a thermodynamically favored process. You could get this reaction to occur, but you would have to put energy in order to cause it to happen. So let's take a look at some more non-thermodynamically favored processes. So these require assistance from outside the system, so from the surroundings, to cause these changes to occur. Water won't boil at 75 degrees Celsius, 1 atmosphere. It won't freeze at 15 degrees Celsius. And iron oxide, if we add it to carbon, isn't going to magically produce carbon monoxide at 25 degrees Celsius. All three of these processes could occur, and they do occur, but just not under these conditions, because they're non-thermodynamically favored at these conditions. Water won't boil at 75 degrees Celsius, but it will at 100 degrees Celsius. So if you raise this temperature to 100, then it would be thermodynamically favored. It doesn't freeze at 15 degrees Celsius, but if you lower it to 0 degrees, then it would be TFP. And iron oxide, rust isn't magically turned back into iron, but this particular process, it's called smelting, can be done at very, very high temperatures, at which case we could get iron oxide and carbon to turn in iron and carbon monoxide. And so all known reactions, have two sides on their coin. They can be either thermodynamically favored or non-thermodynamically favored. And what makes the difference is just the direction they're written in. So for example, if we take a room where it's negative 10 degrees Celsius, if we have liquid water, it will turn into solid water. It's going to freeze. That is a thermodynamically favored process. The same process, though flopped, so solid turning into a liquid, so melting, would not be thermodynamically favored at negative 10 degrees Celsius. We can do this with any reaction. Any reaction that's thermodynamically favored, if we flop it, it would be non-thermodynamically favored. Any reaction that does not occur, that's non-thermodynamically favored, we flip it over, and suddenly it is. As luck would have it, exothermic reactions tend to be TFP, and that's because if we look at our charts again that show the process, remember, exothermic reactions, they start with a high amount of energy, they have to get over the activation energy, and then they wind up at a lower amount of energy. Nature prefers lower energy, so they're going from high energy to low energy. That's why exothermic reactions, ones like this where they start with higher energy than they end with, are typically more thermodynamically favored than their endothermic counterparts. However, that is not to say that all endothermic reactions are not thermodynamically favored, or that all exothermic reactions are. So there is some endothermic reactions that can be thermodynamically favored. And so try and remember these, because these will be important things to remember. For example, liquid water turning into a gas. If you take a bowl of water and you set it on the counter, it's going to turn into a gas. It's going to evaporate even if it's not at 100 degrees Celsius. And that would be an endothermic process, because the liquid water is going to have to take in energy in order to turn into a gas. And so this would be an endothermic process, taking in the energy. But this is thermodynamically favored. This happens naturally. Propane, a liquid, will also evaporate. Once again, it's an endothermic process, but it is thermodynamically favored. And we're not talking about something like sweating here. So when you sweat, that's a liquid that turns into a gas and takes heat from your body. That would be an example of getting assistance from the surroundings. So if this was heat from your body, you would be putting that energy into it. So that's not what we're talking about here. We're talking about isolated systems where this is occurring all by itself. And so this is an endothermic process. It's getting that energy from other places, getting that energy from within the system. Another example of a thermodynamically favored endothermic process would be the dissolving of some salts. So for example, sodium chloride, if you put it into water, is going to break apart into Na and Cl-, which is actually an endothermic process, so it absorbs some energy. It doesn't get that energy from the surroundings, it gets that energy from the water that it's in, so part of the system. But that is a thermodynamically favored process. If you think about salt put in water, it dissolves on its own. We can flip that around. If we think of sodium and chlorine, if we put those in water, we're not going to produce NaCl. This would be a non-thermodynamically favored reaction. Even though technically it would be exothermic, it's not thermodynamically favored. This is the process that would occur naturally on its own. So what is it that makes some endothermic reactions naturally favored? If we think about that chart again where we measure energy, we've got something going from a low state of energy up to a higher state of energy. And so you wouldn't think that would happen naturally. You've literally got something gaining energy and becoming more energetic. So there must be something else that we can tie into this beyond just enthalpy. And it just so happens there is. It's called entropy. So hey guys, start repeating this in your head. Make it a little mantra. There's enthalpy, which is H, and there's entropy, which is S. So make sure you understand the difference between those two and don't get the words confused. So enthalpy is a measurement of heat, energy, that kind of thing. Entropy, on the other hand, though, is a measurement of disorder of the system. So a greater degree of disorder is more favorable. A positive value for delta S, that would be more disorder, and so that would be favorable. And just like enthalpy, we measure this in a delta version. So the change in enthalpy for a reaction would be the enthalpy of the products minus the enthalpy of the reactants. So the amount of disorder for the products minus the amount of disorder for the reactants. And so nature does tend towards disorder. And if we think about like the dissolving process again, if you have a salt cube, you have sodium chloride that is very, very organized. Within this structure, you have a lot of very, very organized Na and Cl molecules rearranged in a pattern. If you put that in water, those NaCl molecules are going to break apart and disorder themselves. They're going to move to a state of very, very disorganized disorder, for lack of a better term. And so this is why the dissolving of salt is thermodynamically favored. Even though it's endothermic, we're going from a state of order to disorder, and that's what nature prefers. Let's think about this another way. Let's say your kid brother is stacking up blocks, and you walk past and you whack that stack of blocks. They're going to fall over and go from a state of order to a state of disorder. And they do that naturally. You gave them a knock, and they move to disorder. However, if you walk past a pile of blocks and you give them a quick whack, do they ever go backwards and form into a pole or form into a stack? No, they don't. Nature tends towards disorder, and it's really, really hard. You have to put lots of energy in to get things to go from disorder to order. You would have to physically take those blocks and stack them to do this process. Just like for dissolving, you'd have to physically go through and take out the sodiums, take out the chlorines, and reform this into it. So if you really stop and think about it, entropy is everywhere. Does your house ever get cleaner as it just sits there? No, it gets dirtier. You have to physically go and clean it. If you make stir fry, you put a bunch of different vegetables in there. As you stir it, does all the broccoli end up on one side and all the snow peas end up on the other side? No, they end up kind of mixed up all together. They enter a state of disorder. So nature naturally goes towards disorder. It takes energy to move things from disorder back to order. All right, 2 laws of thermodynamics that we need to know. The first one is that the energy contained within the universe is constant. Another way of putting this is energy cannot be created or destroyed. And what that means is the amount of energy that we have right now in our universe will never change. We can never get more energy or less energy. So when you go out and you run, the energy that you are using is energy that has been in the universe for a very, very long time. It's just been transferred. You ate food. Well, the food got its energy from the sun, and the sun got its energy from a nuclear fusion reaction, and the energy for that came from something else, and it just keeps going on and on. So energy is not created or destroyed. It just cycles from one thing to the other. And then the second law says the entropy of the universe is constantly increasing. So the universe is getting more and more into a state of disorder. And that makes sense because everything moves towards disorder. And so it's not going to start increasing, it'll start decreasing. Every time that a reaction occurs and we release heat or energy out into the universe, that energy increases the entropy, so it's that SWOT on the pile of blocks, and it becomes more and more disordered. Yeah, I know, it's depressing. Alright, let's recap what we know so far. First off, there was delta H, and delta H represents heat, it represents energy. And when we talk about delta H, we're talking about the change in energy. So if something produces a delta H that's positive, that means it's endothermic. If something makes a delta H that is negative, that means it is exothermic. So in this case, it's a reaction that requires energy. This is a reaction that releases energy. Now we've got a new one to introduce, and that's delta S. So delta S is a measurement of disorder of the system. If we have a change in S, so a change in entropy that is positive, that means it is entering more disorder. And if we have a delta S that is negative, we have less disorder. And this is going to be troublesome, but I'm going to use the terms now. More disorder also means less order, and less disorder also means more order. And so remember it both ways because it's going to be referred to both ways. So if it's positive, think about positive, you're increasing the amount of disorder, so you're increasing the kind of scattering of everything. And if it's negative, that means you're taking things and you're putting energy into it to move them around, back into a more of a repetitive pattern. Now here's a list of things that have a delta S that is greater than 0. That is to say positive. So that's another thing that's worth pointing out. Greater than 0, positive, the same thing. So all of these would be things that are going to be increasing in disorder. And we'll go through and look at each of them individually. So the mo heat, the mo motion. Remember that if we've got something like a solid, so H2O solid, that's ice, we have a very, very organized set of particles. So that would be less disorder than what you would have if you have a liquid. So when it's liquid, we're heating it up, we're getting more motion, and so that motion is going to cause them to slide around past each other. And so we're talking about more disorder. So we go from solid to liquid, we're going from very organized to less organized, which means a small amount of disorder and a larger amount of disorder. And so as a result, we would get a delta S that is positive. And if we take it another step and vaporize it, we've got our liquid where things are moving around, but this is still a relatively low entropy. It's not that much disorder. Things are just kind of sliding around. When we heat it up and turn it into a gas, though, wow, this is a high entropy. Think about those gas molecules. They are bouncing all over the place. I mean, if we had a container that this liquid was in, it's going to stay within that container, so it's fairly organized. But if we have a container and we heat this up, those gas molecules, they ain't sticking around. They're bouncing wherever they want to. So that is a very, very high entropy. So this is even a greater difference in entropy than it was when we talk about the solid to a liquid. So when we talk about solid to a liquid, the change in entropy is greater than 0. But when we talk about a liquid to a gas, the change in entropy is also greater than 0, but it is much, much greater than 0. So the difference, the delta S for this process, would be significantly less than the delta S for this process. And it's because the difference in disorder from this side to this side is just from being stationary to sliding. This one is from sliding to moving all over the place. So much, much more disorder. It can also be just as simple as counting particles. So if we look at this example right here, we start with 4 reactants and we wind up with 29 different products. So we have only 4 molecules on this side, 29 molecules on that side. That's going to be a pretty significant increase in disorder. Now this molecule right here is actually nitroglycerin, and so you can see here why it's so explosive. We go from just a small amount of liquid to 29 different gas molecules, and so that's going to be a huge expansion, a huge change from a liquid to a gas disorder. We're not just going from 4 molecules of liquid to 4 molecules of gas. We're going from 4 molecules of liquids kind of sliding around past each other to 29 different molecules of gas bouncing all over the place, fighting for room. And then we did talk about this one, so dissolving is usually a positive delta S. It's not always the case, but we'll consider that it usually is, and we'll see some examples of ones that are not. So we have an ionic compound like sodium chloride or anything else that is neatly organized, and then when we put it in a liquid, it separates out those guys and they start moving around. So this visual just shows you pretty clearly order, disorder. So an example of something dissolving that does not increase entropy but actually decreases it, so one that winds up with a negative entropy, was when you would dissolve a gas inside of a liquid. So something like carbon dioxide, that's what's in soda pop, it dissolves inside of a liquid. That is a decrease in entropy because you're taking the gas that's bouncing all over the place and then confining it to a liquid. And so inside of there, it's basically turning into, in essence, a liquid, kind of sliding around, even though it maintains its individuality. So that would be dissolving, but it would be a negative entropy. Here's a little chart that shows us how entropy changes with temperature. And so we can see over on our y-axis we have entropy, and down here we have temperature. And this isn't necessarily just water, this is any substance, as it goes from a solid to a gas. So while it's a solid, even though it's still a solid, as you heat it up, those molecules are going to move more and more and more. The more heat, the more motion. So we heat it up, and it's increasing its entropy. And then when it goes from a solid to a liquid, that process is called fusion. And so it's going to just have a sharp increase in its entropy because it's going to go from the fairly organized solid to the disordered liquid. And then the liquid, mo heat, mo motion, gets more disorganized. We come right here, go from a liquid to a gas. That process is called vaporization. Sharp spike in our entropy as we get to a gas, and as you heat gases up, their entropy changes or increases as well. And we could follow the same process backwards. So as we cool things down, they decrease their entropy. And so this Boltzmann distribution just shows us what we talked about. As you increase the temperature, or the average temperature, increasing the amount of kinetic energy within that system. So mo kinetic energy, mo motion, mo entropy. And our last example of something that's going to increase entropy would be changing the volume of a gas. And so if we've got a gas in a small container, it can bounce around, but it can only bounce around so much. But if we increase the volume, it can bounce around more, thus increasing disorder. Okay, so those are all the things that have a positive delta S, and you do need to remember those because you're going to be approached with questions that say, hey, if you dissolve this solid, is it going to have a positive delta S or a negative delta S? And you need to know all of those things that we just talked about. And also remember, if we do any of these things backwards, so if we take a gas and we decrease its volume, then its delta S would be negative. Just like enthalpy, if we flop a reaction, we flop the sign. And so all of the ones that we just talked about, if you kind of flip the conditions, you flip the sign. So those will all be negative as well. So you now know what makes things positive, what makes things negative.